Welcome back to Aurora Tech Channel. Today, I'll be reviewing an industrial 3D printer from Mingda, the MD-400D. Weighing nearly 200 pounds, it's a massive machine. However, the MD-400D is actually the smallest model in Mingda's lineup. Their largest printer boasts a 1 meter cube print volume. The MD-400D has a print volume of 400 millimeters cubed. It's an IDEX printer with 2 independent print heads that can print simultaneously. In addition to printing with multiple colors or specialized support materials, like all IDEX printers, it can print 2 objects at the same time. This printer uses a Cartesian kinematic system featuring 12mm linear rails for the X and Y axes and a 12mm ball screw for the Z axis. It's also one of the first IDEX machines to utilize KLIPPER firmware. Both print heads feature direct extruders with bowed-in tubes that guide the filament from the enclosed compartments to the print head. The hot ends are high-flow models, boasting a maximum flow rate of 40 millimeters cubed per second. The nozzle temperature reaches up to 350 degrees Celsius, and the heated bed goes up to 110 degrees Celsius. The bed itself is a 10mm thick solid aluminum plate, significantly thicker than the 3mm plates typically found in hobbyist machines. Beneath the PEI sheet, there's a tool height gauge for setting the Z offset between the 2 extruders. Additionally, a macro camera assists in setting the X and Y offsets directly on the screen, eliminating the need to print test patterns repeatedly to calibrate the extruders. For auto bed leveling, the MD-400D uses a new bed distance sensor. Unlike traditional BL touch sensors, inductive probes, or strain gauges, this sensor doesn't move up and down during probing, allowing it to scan the bed at high speed. The bed distance sensor and an accelerometer for input shaping calibration are installed on the primary extruder. Aside from these additions, both extruders are identical. For part cooling, each print head is equipped with dual 4010 blowers, and 2 powerful auxiliary fans provide additional cooling from the back. The printer runs on a Linux-based OS with KLIPPER firmware, featuring the standard KLIPPER screen interface. Firmware and screen UI updates can be performed directly via the Mainsail web interface, which is also accessible through Orca Slicer. In this video, we'll run a series of benchmark test prints to evaluate clearance, retraction, tolerance, and surface quality. We'll also test a range of materials, including printing PLA with PVA support, PET carbon fiber with high temperature support, and parts made from PETG and TPU. I would like to thank Mingda for sending us this machine and for sponsoring today's video. Even though it's a sponsored video, we will provide an unbiased review and won't hesitate to point out any cons. With that said, let's get started. The machine arrived in a sturdy wooden crate weighing close to 230 pounds, with the machine itself accounting for about 190 pounds. Due to its huge size, we had to be very careful and it took a lot of work to move it. Assembly is not needed though, just remove the accessories box from inside. The box includes a signal bulb, various tools, spare nozzles, a steel calibration plate, and a Wi-Fi antenna. The signal bulb attaches to the top of the machine, offering a clear visual indicator if the machine runs out of filament or pauses mid-print. The Wi-Fi antenna screws into the back, and there's also an Ethernet option for network connectivity. When the machine first turns on, a Linux OS boot screen appears, followed by the KLIPPER interface. It's a bit unusual to see the full user manual, consisting of 43 pages, displayed on the 7-inch screen. I doubt anyone would read it there, especially since a physical manual is also provided, but it doesn't hurt to have it as an option. I decided to skip it. The machine then prompts you to select the time zone, after which you can re-level the bed. However, since this is done through the KLIPPER screen UI, I opted to do it later. After connecting to my Wi-Fi network, the main menu of the KLIPPER interface appeared. I went to the calibration menu, starting with Z Calibrate, which involves setting the Z offset. As this machine doesn't support auto Z offset, you need to manually adjust the distance up and down using a piece of paper and the touchscreen. For auto leveling, since this machine uses a bed distance sensor, it operates much faster than a regular inductive sensor, BL touch, or strain gauge. It probes 15 by 15 points, 225 in total, and each pass takes only 25 seconds. The machine completes 2 passes, and the entire process finishes within a minute. For the X and Y offset, we need to remove the print surface and put a small steel plate at the center to protect the magnetic sticker. The print head then moves to the camera at the back, where we use the touch screen to align the center of the primary extruder with the cross. Afterward, we repeat the process for the second extruder. For the Z offset between the two extruders, the machine uses a tool height gauge. The primary extruder moves down to trigger the gauge, followed by the secondary extruder, allowing the machine to determine the height difference between them. In my case, the difference was minus 0.15 millimeters. Then, we calibrated the input shaper, starting with the x-axis and then the y-axis. The frequency testing results were visible in the mainsail web interface. For Z-Pro position, I will not adjust it for now, as both extruders can trigger it without any issues. Okay, we can now load the filaments and start our first print. I loaded both extruders with PLA for some benchmark tests. Starting with the 3D Benchy, I printed the file in copy mode, so both extruders printed simultaneously, producing 2 Benchies. It seems the Z offset is a bit low, and the first layer speed is not as fast as most Clipper printers. The speed increased after the first 2 layers. I let it print a few more layers and conducted a sound test. The sound meter, placed 6 inches away from the machine, recorded around 70 decibels with the door open. The loudest noise came from the fans, and I could feel the airflow from the auxiliary fans even when standing a few feet away. When fully enclosed, the sound level dropped to the low to mid-50s, which is much quieter. Including heating and prep time, the print finished in 51 minutes. For a Benchy printed at this speed, I wouldn't consider it fast, and the result was just okay. Stringing was minimal, and cooling performance was good, but the surface quality wasn't particularly clean. From the top, it looked fine, with no signs of under-extrusion. Overall, I assume everything is working as expected. We will now do our benchmark prints, starting with the number slider to test the clearance. Since the Z offset of the first print was slightly too low, I increased it by 0.06 millimeters using the screen, hoping the first layer would have better clearance. The print finished in 3 hours and 35 minutes, which is slower than the average printing time of 2.5 to 3 hours on other Clipper printers. The top looks fine, with almost no stringing, and the text is clean. However, at the bottom, some tiles of the red slider were stuck together and required a gentle slap to separate them. The green one looks perfect, with all tiles moving freely. After manually separating the stuck tiles, the red one also functions fully. Next, I printed the mini Honeycomb box to test the retraction of both extruders. This print took about the same time as other Clipper printers, as the small size of the print leaves little room for acceleration, even with an acceleration setting of 3,000 millimeters per second cubed. All the Honeycomb patterns printed without breaking, but there was slightly more stringing than expected. The bottom of the print looks fine and mostly clean. Then, I printed the tolerance model and see if the parts can fit together. The print finished in 2 hours, which is consistent with other Clipper printers. On the square side, it cleared all the way up to 0.05 millimeters, but got stuck at 0 clearance. Similarly, on the cylinder side, it cleared up to 0.05 millimeters and got stuck at 0 clearance. The clearance test for both sides achieved a perfect score. Next, I printed the Robo Alpaka to test the surface quality. Since there is plenty of room for acceleration in the middle of the model, the acceleration speed of 3,000 millimeters per second squared is noticeably slower than average. The print finished in 7 hours, which is much longer than the average 4.5 to 5 hours on other Klipper printers. The surface quality is acceptable, not the best, but not the worst, just about average. When compared with another IDEX printer, the Snapmaker J1S, the MD-400D produces better quality and slightly faster printing time, likely due to the J1S using Marlin firmware. In comparison to the Prusa XL was about an hour faster and produced significantly better surface quality. Looking at the fastest Core XY printer, the Sovol SV08, the surface quality between the two machines is similar, but the SV08 is more than twice as fast. Similarly, when compared to the Creality K2+, the K2+ is also more than twice as fast and delivers superior surface quality. Let's try some other materials, starting with PETG. I needed to print a large base for another model, requiring a bed size of approximately 380 millimeters. Only a few machines in my collection can handle a print of this size. While printing with PETG, I noticed that the previously set Z offset for PLA was too low, causing the first layer to be overly compressed. However, I decided to let the print continue. The print finished in 5 hours and 20 minutes. I printed this model with 3 walls and 3 bottom layers, and the result looks decent, except for the overly compressed first layer. Since I plan to place another model on top of it, the issue won't pose a problem. I printed another standard size pen holder using the same Prusa Filaments PETG. This time, the print took 4 hours and 26 minutes, which is about 45 minutes slower than the average printing time of 3 hours and 45 minutes. The surface quality looks alright this time, with no stringing at all. I didn't adjust the Z offset, so the bottom layer is still slightly too low, but it's not very noticeable. Next, I printed some ABS. The temperature in my garage is quite cold, around 18 degrees at night. But with the machine fully enclosed and the bed set to 110 degrees Celsius, the internal temperature reached over 40 degrees Celsius once the print started and remained steady throughout the print. The print finished in 4 hours and 42 minutes. It turned out well, with no warping or cracking. I didn't apply glue to the print bed, as the textured PEI sheet provides excellent adhesion when it's new. The bottom layer is still slightly too low, even after adjusting the Z offset by 0.06 millimeters, but it's within an acceptable range. I will now print some PLA with PVA support. I'll use the PVA as a support interface, as PVA filament is quite expensive. A half-kilogram roll costs around $35. This roll of PVA was brand new and opened just before the print started, but it still exhibited significant stringing. The print finished in 2 hours and 28 minutes. Although the PVA filament is marketed as water-soluble, in my experience, this white-colored PVA doesn't fully dissolve. However, soaking it in water makes it easy to remove. After soaking for 12 hours, the PVA detached effortlessly. The wings of the dragon are thin, but they printed well with PVA support. The tail also printed nicely after the support was removed. Some PVA residue remained stuck to the model, but using a toothbrush in warm water would help clean it off more thoroughly. Then I printed a set of orthotic insoles for my dad. I used PETG for the bottom to provide better support, and TPU for the heel position and top layer. Since the default profile for TPU is set to a flow rate of only 3.6 mm³ per second, the print speed was effectively 45 mm per second. The print took 8 hours and 48 minutes to complete. The result was very good. It printed exactly as I intended. I had to remove the PETG support from the arch area, but once that was done, the insoles were fully functional. Printing these with PETG and TPU saved my dad hundreds of dollars, as custom orthotics of this kind are typically very expensive. Mingda also sent me a spool of PET-CF and high-temperature breakaway support filament, so I decided to print an adjustable wrench from 3dprintedhardware.com. The print finished in 2 hours, 22 minutes. Printing with this high-temperature support filament generates quite a lot of residue, but fortunately most of it was wiped off on the prime tower. If this model were printed using the same type of filament for support, it would be virtually impossible to remove the support completely. However, with the breakaway support, I was still able to remove most of it and make the wrench functional. Finally, I printed a PLA sheet to test the first layer. After printing with high-temperature filaments, I manually readjusted the Z offset to ensure it was correct for PLA. The print took 1 hour and 6 minutes to complete. The PLA sheet was printed beautifully. The entire sheet peeled off cleanly without breaking. With the Z offset adjusted correctly, the printer was able to deliver a perfect first layer, and both the top and bottom surfaces turned out really nice. Okay, let's talk about the pros and cons of this printer, starting with the pros. 1. The robust build, featuring a steel structure and metal enclosure, weighs approximately 190 pounds. The motion system uses linear rails on the X and Y axis, along with a 12mm ball screw on the Z axis. It is sturdy enough to reliably move the platform, which is constructed using 20x40 aluminum extrusions. 2. Dual print head calibration. The X and Y offset using macro camera. This is so far the best alignment system I have ever tested on an IDEX machine. Unlike hobbyist IDEX 3D printers, you don't need to print the alignment pattern multiple times to adjust the X and Y offsets. Using the pressure gauge to set the Z offset between two print heads is also accurate. 3. An independent dual print head can increase productivity by printing 2 copies at a time. When used to print support material or with multiple materials, it won't waste large amounts of filament like other single extruder multiple filament systems. Since engineering grade and high temperature support materials can be pricey, cost savings can be significant in the long term. 4. It uses a 10mm thick solid aluminum heater bed, while a regular 3D printer uses a 3mm one. The increased thickness improves heat distribution across the surface, reducing warping, especially on larger prints. The added rigidity also makes the bed more resistant to bending or warping over time. The thicker bed retains heat more effectively, improving energy efficiency by minimizing the need for frequent reheating. 5. Super fast bed leveling is achieved using the bed distance sensor, which operates on a 15x15 grid covering 225 points. Instead of moving the print head up and down to probe each point, the sensor scans the surface, completing the auto-leveling process in just 1 minute with 2 scans. By comparison, achieving the same level of detail with a regular inductive sensor or strain gauge probe would take at least 10 times longer to probe the same number of points. This sensor is not only fast, but also highly accurate. 6. There are also several minor improvements and convenient features. The eMMC has been upgraded from 8 GB to 32 GB, the processor has been enhanced to a 6-core from a quad-core, and the machine now supports auto power off after a print is completed. Additionally, it includes a large signal bulb at the top to alert you if something goes wrong with your print. Now for the cons. 1. It has no heated chamber. As an industrial 3D printer, I would expect the machine to support a broader range of materials with a higher nozzle temperature, higher bed temperature, and a heated chamber. For now, the maximum nozzle temperature of 350 degrees Celsius and bed temperature of 110 degrees Celsius don't provide a significant advantage over some non-industrial machines in terms of material compatibility. 2. The machine lacks an auto-Z offset, requiring the traditional method of using a piece of paper to set the distance between the nozzle and the bed. This approach is not only less accurate and consistent than using a sensor. When switching between materials with significant temperature differences like PLA and ABS, due to heat expansion of the bed and nozzle, you have to fine-tune the Z offset while printing, or ideally recalibrate the Z offset through the screen menu before starting the print. 3. Unlike the Bambu Lab X1 Carbon and Creality K2+, they have a micro lidar or second camera on the print head to calibrate flow and pressure advance for different filaments. For this machine, you still need to print a pattern to calibrate it manually if you want to get good results on some models like the tolerance test print. 4. The default print profile is configured for a speed of 200 mm per second with an acceleration of 3000 mm per second squared. While this speed is slower than average, the surface quality, though acceptable, does not meet the exceptional standard one might expect from a machine with robust hardware operating at this slightly reduced speed. This suggests that the input shaper algorithm could further optimize to enhance both print quality and speed, fully unlocking the machine's potential. 5. Like all other IDEX printers, when printing in copy or mirror mode, the Z offset between the two extruders cannot be automatically compensated. The Z axis only adjusts to correct the Z offset in normal mode. To address this limitation, manufacturers could consider adding a stepper motor to the second extruder to independently control its Z height. This design, similar to the motorized Z-axis in a CNC machine or laser engraver, would allow the second extruder to align with the primary extruder by moving itself up or down, rather than relying solely on the movement of the print bed or the Z-axis of the machine to compensate for the difference. In conclusion, as an IDEX printer, the Mingda MD-400D offers distinct advantages for tasks requiring engineering-grade materials with high-temperature support, capabilities that are beyond the reach of hobbyist printers. It can also handle jobs like combining PETG and TPU, which can be challenging for single extruder multi-filament systems like the Bambu Lab AMS and Creality CFS. In terms of hardware, weight, and robustness, it is undoubtedly an industrial-grade machine. However, it lacks some of the modern and convenient features found in higher-end hobbyist machines. At the $5,000 price point, a more feature-rich offering would justify the price tag even more, as the machine still has plenty of internal space, and I believe Mingda could enhance its functionality by adding modules such as heater for the chamber, as well as for the filament compartments to work as filament dryers. If you're in the market for a robust, fully enclosed IDEX 3D printer with a 400mm cube build volume running standard KLIPPER firmware, I put a link to Mingda's website under the video description. Be sure to also check out my website, auroratechchannel.com, for the latest recommendations and 3D printer price tracker to spot great deals. That's it for this video. If you found this video helpful, please give it a like and consider subscribing to our channel. Thank you for watching, and I will see you next time.